Alright, well, we're going to take a look at the classwork chat for the Chapter 10 and 11 review. So, a few of the problems that we'll be doing on this page at least are number 7 and 8. So, first problem, number 7. So, as we read this problem, we need to look for the reactants in the product. So, it says a piece of lead, and lead, the symbol for lead is Pb, is added to aqueous solution. Aqueous just means it's in a water solution of silver nitrate. So from there we can get our two reactants. So we have Pb is being added to silver nitrate. Now it says here that when it reacts with it, it's going to replace the silver to form lead 4 nitrate. So lead 4 nitrate means that we're going to have our arrow, and then on the right side of the arrow we will have the lead 4 nitrate. When it says that a silver precipitate forms, that just means that it's going to give off silver. Now, if you remember, this would be a single replacement reaction because the lead is replacing the silver in the reaction. Now, the first part was just writing out the equation. The second part is balancing. So when we balance, we have to start looking for a few things. First, I see that on the right side I have this NO3, and that's in parentheses, and on the left side I have the same thing, but it's not in parentheses. So I'm going to start by putting that one in parentheses. So now that I've done that, I'm going to start balancing. I see that on the right side I have 4 of the NO3s, but on the left side I only have 1. So what I'm going to do is I'm going to put a 4 out front here. So that 4 means that now I have 4 silvers and I have 4 NO3s. So now that I have 4 silvers, I need to come over here and put 4 silvers. Now we can double check. We have 1 lead on this side, 1 in the products, so the leads are balanced. We have 4 silvers on the reactants, 4 silvers on the products, so those are balanced. And we have 4 NO3s, 4 NO3s, so those are balanced, so this equation is balanced. Okay, now for question number 8. For question number 8, we need to identify what the problem is giving us. It says we're starting with 5 moles of silver nitrate. So we have 5 moles of silver nitrate. That's what the problem is giving us. That's the information that's being given. We know that because it's giving us an actual number there. And then the question is asking how many moles of lead are needed. So this is a mole problem where we have to convert from moles of silver nitrate into moles of lead. So we start by setting up the problem. The moles of silver nitrate is what we're starting with. So we have 5 moles of silver nitrate. So silver nitrate is just AgNO3, and we get that from the top part of the problem. Now we set up our conversion factor, and we set it equal to, and as we set up here, the question is asking for moles of lead. So our units that we're going to end with are moles of lead, moles Pb, just like that. Now, in order to solve this problem, we know that we're starting with moles of AgNO3, and we want to somehow get rid of those. So how do we get rid of those? We could assume that this one is written over 1 just like a fraction, even though the 1's not written there. So just how you would in regular algebra, if you want to cancel off this unit right here, you have to first write it underneath the fraction bar. So we're going to write it underneath over here. So moles of AgNO3. Now when we do that, that's going to cancel off our units, but what do we want to end with? We have this over here, that's what we want to end with, so we have to write that on top. So moles of lead on top. Now what we have to do is plug in our numbers. Where do we get the numbers? We get those from our coefficients above. So from this equation up here, we know that the coefficient in front of Pb is a 1. Even though it's not there, we know it's a 1. So we put a 1 up on top, and then for AgNO3, we found out earlier that it was a 4, so we put a 4 down here. Now it's just simply doing the math. Okay, and we already said that these units cancel off with the units over on the left. So now we have the math 5 times 1, which is just 5. And so then we go 5 divided by 4, and that's going to give us 1.25 moles. And that is our final answer for this problem. For part B, we do it similarly. We identify what the problem gives us. It gives us 3 moles of lead. and it's asking for moles of silver. So we start with 3 moles of lead, set up our conversion factor, and then the question is asking for moles of silver, so we put moles of silver over here. And now we just start doing the problem the same way. Again, we want the moles of lead to cancel off, so we're going to put moles of lead down here because now algebraically those units get canceled off. And then the units that we want to be left with are moles of silver, so we put moles of silver on top, and now we just fill in the numbers using the coefficients. The coefficients from up above for silver is 4, so I put a 4 there, and then the coefficient for PB is 1. Now all we have to do is do the math. 3 times 4, that's going to give us 12, so our final answer is 12 moles of silver. Okay, the next 2 problems that we're going to do are on page 2. We're going to do numbers 11 and 12. So looking at 11, this is a complete combustion problem. So the thing that we're starting with is C4H8, and this is a complete combustion, so that means we are reacting it with oxygen gas, O2. So anytime we have a combustion reaction, remember it's O2, so the gaseous form of oxygen. Draw a little reaction arrow, and if you remember, the 2 products of a complete combustion reaction are H2O and CO2. So those are our 2 products. So this is for the complete combustion of a hydrocarbon with oxygen. That's our equation. Now we have to balance it. Okay, we notice that on the left side we have 8 hydrogens. On the right side we only have 2. So that's going to be the first thing I'm going to balance. In order to get 8 hydrogens on the right, we're going to need to put a 4 right here as a coefficient. When we put a 4 there, we now have 8 hydrogens on the right, 8 hydrogens on the left. The hydrogens are balanced. So now let's look at the carbons. Carbons, I see that I have 4 carbons on the left, but I only have 1 carbon on the right. So that's going to be the next thing I balance. In order to balance the carbons, I put a 4 on the right side next to CO2. Now the carbons are balanced. The only thing that remains are the oxygens. If I count these up, on the right side I have 4 oxygens here, plus another 8 oxygens here. So on the right side of the equation, I have 4 plus 8 is 12 oxygens total. So in order to balance the oxygens, I need to put a 6 here, because now that will give me 12 total oxygens on the left, 12 total oxygens on the right, and when I do that, all the atoms in this equation are balanced. Okay, this next problem is going to be the same thing. We're just simply doing the combustion of acetone. Okay, now that we have the equation set up, first thing we're going to do is look to see what atom we're going to balance. I see that on the left side we have 3 carbons, on the right side we have 1 carbon, so in order to balance that, first thing I'm going to do is add a 3 as a coefficient here. Now I have 3 carbons on the left and 3 carbons on the right. Okay, the next atom I'm going to look at are the hydrogens. I notice I have 6 hydrogens on the left, and I only have 2 hydrogens on the right. So in order to balance the hydrogens, I'm going to put a 3 right here, because that 3 gets multiplied by that 2. And so now on the right side I have 6 hydrogens, on the left side I have 6 hydrogens, so at this point the hydrogens are balanced. The only atom now that remains to be balanced in this equation are the oxygens. So now I look over here, using this part right here, I have 3 oxygens. Over here I have 6 oxygens. So total on the right side I have 3 plus 6 is 9 oxygens. So I'm just going to write that up there. We'll save that for later. Now on the left side, I have to remember that I have this little oxygen right here, so that already counts for 1 oxygen. So now the difference is that I have 9 oxygens on the right, I have 1 oxygen on the left, plus I have this one right here that I'm going to need to change a coefficient for. I don't want to change this coefficient because that's going to change my carbons and my hydrogens, and I don't want to do that. So what I'm going to do is come up with some number that I can put right here so that it's going to give me 9 oxygens on the left. So basically what we do to figure out how many oxygens we want from this molecule, I'm going to take 9, which is the total number of oxygens on the right. I'm going to subtract the 1 that comes from this oxygen right here, and that's going to give me 8. So from this molecule of oxygen, I want to get 8 oxygens total. So how do I get 8? I just simply put a 4 right there. When I put a 4 there, now my oxygens are balanced. I have 9 oxygens on the left and 9 oxygens on the right. Now, for problem number 12, we're going to set it up the same way. We have C4H8. It's a combustion reaction. This time it's an incomplete combustion reaction. So we are going to be reacting it with oxygen still. That does not change. The thing that changes is that instead of producing CO2, how we did in the last problem, we now are just producing carbon monoxide, CO. But our other product that we're going to be producing is water. So that part stays the same as well. First thing I'm going to look at are the hydrogens. I see that I have 8 hydrogens here, 2 on the right. So in order to balance hydrogens, I'm going to put a 4 right here. That balances my hydrogens. Then the next one that I'm going to balance is the carbons. I see that I have 4 carbons on the left and only 1 carbon on the right. So I'm going to put a 4 here, and now that balances my carbons. So if we double check them, we have 4 carbons on the left, 4 carbons on the right. Those are balanced. 8 hydrogens on the left, 8 hydrogens on the right. Those are balanced. So that leaves us with the oxygens. From this molecule right here, we have 4 oxygens. From this molecule right here, we have another 4. So that means that our total number of oxygens on this side are 8. So now we need to put a number here so that our total oxygens on the left side will be 8. Since we have a 2 right there, that number is a 4 because 4 times 2 equals 8. And now our equation is balanced. Now part B can be a little bit trickier. So I'm just going to start by writing our equation how we had it in the first problem. But remember, instead of having carbon dioxide, we're going to have carbon monoxide. Now, to start this problem, I see 3 carbons on the left, 1 carbon on the right. That's going to be the first thing I balance, so I put a 3 here. Carbons have 3 of them on each side. Next, I go to the hydrogens. I see I have 6 on the left, and I only have 2 on the right. So to balance my hydrogens, I'm going to put a 3 here, and now my hydrogens are balanced. This is where it gets tricky. On the left side of the equation, I have 1 oxygen over here. So 1 oxygen's here, 2 here. That means I have 3 oxygens on the left side. On the right side, I have 3 oxygens here plus 3 oxygens here. So on the right side, I have 6 oxygens. Now, as I said, I have 3 oxygens on the left, 3 on the right. But I don't want to change this coefficient, because if I change that, that's going to change my carbons and hydrogens, and I'm just going to start working backwards. So instead, I need to add a number here. So we said that we have 6 oxygens on the right, and we have 3 oxygens on the left side of the arrow, but we have this 1 oxygen right here. So in order to figure out what number goes here, we take the 6 from the left, and I'm going to subtract the 1 from this oxygen, and that leaves me with 5. So I want to put a number right here that makes this whole molecule give me 5 oxygens. So what am I going to do? I'm going to put a 2.5 because 2.5 times 2 equals 5. When I do that, I now have 6 oxygens on the left and I have 6 oxygens on the right, and yes, this equation is balanced. However, it is not finished. We cannot leave an equation with a decimal number. Okay? A balanced chemical equation cannot have a decimal number, so the simplest way to get rid of that decimal number is to simply multiply every coefficient by 2. When we multiply the first coefficient by 2, we get a 2. When we multiply the next one by 2, we get a 5. When we multiply the next one by 2, we get a 6. And then when we multiply the last one by 2, we get another 6. And that is our balanced chemical equation. The next problem that we will be doing is question number 14. So with this problem, we have this part would be as our reactants, and then it says that we are going to be doing a double replacement reaction. So that means we need to first figure out what our products will be. So I start by writing my FeCl3. This is going to be added to NH4, PO4, and then my products, so I'm going to draw this down here so I have room. My products are going to be formed when the Fe replaces the NH4. So we can start by writing this as FePO4 as one part of our products, and then the second part will be NH4Cl3. From here we see that simply this Fe came in and replaced this NH4, and that's all that we did here so far. But we haven't changed any subscripts. Okay? So we have changed some subscripts, but we need to go back and figure out what subscripts we are going to keep. Okay, one thing I just noticed is that I want to clarify this NH4 right here is in parentheses, so we can put the parentheses here. That's why that subscript does not change. Similarly, we can put this PO4 in parentheses because that's a polyatomic ion, and that means we don't want that 4 to change. However, there's one subscript that I did add that wasn't supposed to, and that's this one right here. That Cl should not have a subscript yet. Now, in order to get the subscripts, we need to figure out what the charges are on each one. Now, if we look at chlorine over here, chlorine is in group 7A, so each chlorine has a -1 charge. But there are 3 chlorines, so that means this chlorine, there are 3 negative charges from that chlorine because it has a 3 down there. So because you have 3 negative charges and this whole molecule right here is neutral, we have to have a +3 over there. Similarly, if we go to the NH4, we know that NH4 is a polyatomic ion and it has a +1 charge, and we have 3 of them, so there's 3 +1 charges. Because of that, we know that this PO4 has a -3 charge. We're going to use that information to get our subscripts. So we come down here to our product side. We know that this PO4 has a +3. It has a -3. And this Fe has a +3. The +3 and the -3 cancel off, so we could leave those subscripts as 1 and 1, or we can just not write them. Now we come over here, we double check this. NH4 has a +1 charge. Cl- has a -1 charge. Those charges balance out, so we can just put our subscripts of 1 down there, or like I said, leave them off. Now what we do is double check and see which one of our options, A, B, or C, matches our answer. And so on this problem, the correct answer is B. Now, A is wrong because for part A, this Cl3 has a negative charge. Negative ions should not be written first. Similarly, we see the same thing happen down here. That's just one of the multiple things that are wrong with these. Also, this PO4 has a negative charge as well, and we know that 2 negatives do not bond together. Same thing on this side, we have a positive and a positive. 2 positives do not bond together, so that's why A is wrong. C is wrong. We already said that the negative is written first, followed by the positive. Over here we have the negative ion written first, followed by the positive. That's why C is wrong, because it always is written as the positive cation first, followed by the negative anion, and that is seen in every single one of these compounds. Alright, so the last two problems we're going to do part of this video are numbers 17 and 18. Number 17, this is just comparing standard temperature and standard pressure. These are just numbers that you'll be expected to know. We won't be using these as much this semester, but next semester these numbers are going to become very important. Now, these did come from one of your sets of notes, but we didn't talk about all the possible values. So just quickly, I just want to give you all the different values for standard temperature and pressure. We have 0 degrees Celsius, we have 273 Kelvin, we have 1 atmosphere of pressure. So before I do that though, remember these right here are the standard temperatures. Now the standard pressures, we have 1 atmosphere, we have 760 millimeters of mercury, and we have 101.3 kilopascals or kPa. Now remember, when we talked about 1 mole of gas, we said that 1 mole of any gas, so any type of gas that we could have, when it is at STP, so meaning it is at any one of these temperatures and pressures, so 0 degrees Celsius or 273, these two are actually equal to each other. So it's the same temperature, same thing. These three are all the same pressure, just different units. So whenever a gas is at STP, so it's at this particular temperature and this particular pressure, then we can say that it equals 22.4 liters. And we have to use that information to answer the problem below, number 18. So let's look at A. A says we have 1 mole of gas, 22.4 liters, at 0 degrees Celsius and 2 atmospheres. What is wrong with that statement? The 2 atmospheres. That is incorrect. That makes A wrong. Next, we have B. B says we have 1 mole of gas, so again 1 mole, it's at 22.4 liters, at 0 Kelvin, and 1 atmosphere. What's wrong with this? It's the value of STP, so they gave us the wrong temperature. So it's not 0 K, it's supposed to be 273 K. That makes B wrong. For C, we look at this, we have 1 mole of gas, 22.4 liters, 273 K, 760 mmHg, everything there looks good, so this statement is true, so we can circle that one. Same thing for D, we have 1 mole of gas, 22.4 liters, 0 degrees Celsius, 101.3 kPa, those are at STP, so that equation is true as well. And finally, this one could be a little trickier. Before we do the first part, let's just check our STP. We have 0 degrees Celsius, 1 atmosphere. That fits under STP, so that part of this statement is true. Now, let's see. What 2 moles of gas is equal to 44.8 liters? We know that 1 mole of gas equals 22.4 liters. So it is true that if it's still at STP, then 2 moles of gas does equal 44.8 liters at STP, making this statement true as well. So according to that, all three C, D, and E are true. Now, this concludes the first part of the video. I'll go ahead and post this, and then the second part of the video, which will include question number 19, 20, 21, 22, 23, 24, and number 25, parts C and G, that will be posted later on. So hopefully this helped you out, and good luck studying.